Hello and welcome to another video by HPart. In our last video, we split the lens to reduce our spherical aberration and improve our overall collection efficiency. By the end of the video, we'd managed to get it up to about 70%. But we noticed that there was still a lot of light, and it looked pretty blue, that was missing the fiber. In this video, we're going to investigate why that's happening, and then we're going to fix it. Let's get started. First thing we need to do is duplicate this design so that we have a space to work in. Now let's recompute the collection efficiency and make sure it's still at about 70%. It is. Okay. Now let's zoom in on this offending bluish cone over here. Now if we take a look at these rays of light, it looks like they're focusing right about here, just a few millimeters above or in front of the detector. To confirm that suspicion, we are going to create a point source emitter over here, and we're going to launch from it a single red ray of light and a single blue ray of light through these lenses and see where they hit. So let's go ahead and do that. Put this up at maybe 12, back a little bit. Okay, so there's our point source emitter that we're going to shoot the light out of. Now we're going to create two single ray emissions. One that is violet, or blue, and another one that is red. And we're going to modify our display preferences once we cast these guys. We've casted them. Go ahead and modify our display preferences to hide the uniform infinite emission. And what we notice is we don't see any rays of light. Now why is that? Well, it's because when we created them, we didn't actually add a light path to them, so the rays that they were emitting got classified as stray. So now we've added that light, we can go ahead and cast it again, and sure enough we'll see them, but they're pretty faint. So we'll pop up the display again, we're going to turn on the hit markers, and here we go. So now we can clearly see what we suspected earlier on. We've got a violet ray that's down here, and a red ray that's above it. And if we were to trace that back, the violet ray would intersect itself somewhere in this area, whereas the red ray is making it all the way into the detector and intersecting roughly on the detector. So this is a big problem. The question is, why is this happening? And the answer comes down to the physical properties of the material that makes up these lenses. To understand that better, I'm going to move this over a bit, and then I'm going to open up the materials panel. And I'm going to search for NBK7, which is the optical glass that we use to make these lenses. Now, scrolling down here, we can see that there's a dispersion curve. And the dispersion curve plots the index of refraction versus the wavelength. And what we can see is as the wavelength gets smaller, the index of refraction starts to rapidly increase. Now, the greater the index of refraction, the stronger the glass bends the light. So this curve is just a precise mathematical expression of the phenomenon that we've observed here. The lower wavelength light, around 400 nanometers, has a higher index of refraction, so the glass is going to bend it more strongly, and so it's going to end up down here, and its focal point will be closer to the lenses than we want. This phenomenon occurs with nearly all optical glasses and is called chromatic aberration. And it's just a name for the consequence of the dispersion curves of most optical glasses being shaped like this. Now you might be asking, why do most optical glasses have a curve that looks like this? And the in-depth answer is a little bit beyond the scope of this video. But the long and the short of it is that most optical glasses have resonance peaks in the ultraviolet. And at a resonance peak, the refractive index skyrockets. And so what you see here is the curve gently rising and then rapidly rising towards a resonance peak somewhere out in the ultraviolet. So now that we know the name of this phenomena, chromatic aberration, and we know that it comes from the shape of this dispersion curve, and any glass that we pick is likely going to have a dispersion curve that looks like this. It raises a very important question. How do we fix it? Now, to answer this question, We're going to start from first principles and consider the options that we have. We currently have two lenses, which we split from one positive power lens. So we're going to think of both of these lenses as effectively one positive power optical unit. And we created it to focus the collimated light to a single point. So we can't really change the power of this lens, because if we do so, then we're no longer going to be focusing where we want. We could change the material that the lens is made out of to be something that was less dispersive, and that would make things better, but it wouldn't entirely eliminate the problem. So what other options do we have? Well, we could try adding an additional lens. Now, if we did that, we've got to wonder, well, what is the lens supposed to do? Well, when we add the lens, we've got three options for it. It could be a positive power lens. It could be a flat lens with no power, or it could be a negative power lens. If the third lens that we add, say somewhere over here, had positive power, then it would end up pulling this ultraviolet ray even farther down. It would do the opposite of what we want. If we added a flat lens, it wouldn't do much at all. And if we added a negative power lens, it would actually push the ultraviolet ray up. It would disperse it. And that's actually closer to what we want to do. We want to raise the ultraviolet ray up. But we want to do it without moving the red ray, which is already in the right position. Now, we're not going to be able to find an optical glass that will move the violet ray without moving the red ray. But we can find a lot of optical glasses that, at least relative to the glass we're using currently, will move the violet ray much more than they'll move the red ray for a given amount of optical power. Now, this means that if we put a negative element out of one of these glasses, roughly right about here, and only have it be slightly negative, it will still have a much larger effect on the violet rays and will disperse them much more than it does the red rays. And we can then balance that effect out by increasing a little bit the positive power of our existing NBK7 lenses. And if we do it right, we can get both rays to land at exactly the same spot. Now, this counterintuitive idea of using an optical glass with more dispersion to solve the problem of dispersion is called an achromat. So now, let's build one. To build an achromat, we first need to find the glass that's going to make up our third lens. Now, this glass is characterized by having higher dispersion than our NBK7. So we need a way of searching for glasses that have a greater amount of dispersion. And fortunately, there's a number that summarizes this for us, and that number is called the ABA number. Now, the formula for the ABA number is given as follows. It's a ratio. In the numerator, we have the yellow helium line, which is at around 587, minus 1, divided by the difference between the blue hydrogen line at around 486 minus the red hydrogen line at around 656. Now, the way to think about this is you basically are taking the index of refraction at the middle of the visible range, and you're using that to normalize the value. But the real action is happening in the denominator. In the denominator, we're taking the difference in the index of refraction at the blue end of the spectrum versus at the red end. So the greater this difference, the more dispersive the glass is. Put another way, the larger this difference, the smaller the V number. So small V numbers are highly dispersive, large V numbers are not. So what we need to do is we need to select a glass that has a small V number. And for this, we're going to go with a glass called NF2, which is a classical choice. Let's go ahead and pull this up. And what we can see is the curve actually looks pretty similar. It is a little steeper, but it's really shown by the V number, which is all the way down at 36. And the refractive index is much higher. So for a given amount of curvature, this is just going to bend all the light more, and it is especially going to bend the blue light. So this is what we've been looking for. Now that we've selected our glass, let's go ahead and add our third lens. So first thing I'm going to do is just go ahead and create this lens. It's going to be a meniscus lens. So it'll be a negative power lens that's going to sit right on top of the lens that we already have here. And I'm just going to go ahead and let's see, I'm going to rotate it, and I'm going to select our material in F2. And I'm going to go ahead and create it. As you see, the lens we just created is actually sitting on top of our first lens. So we need to fix that. We need it to sit right here, regardless of how this lens changes. So for that, we're going to use a formula, and we're going to use the spacing formula builder. Now you could manually create this formula. It's not that hard, but using a formula builder is just a lot faster. So I'm going to anchor it to body 2, and then I'm going to select body 3, which is the lens we just created, and I want the spacing to be 0. So now the lens is sitting right there, but we can still see a lot of overlap because the radius of curvature of this lens, our second lens, is different from the radius of curvature of our third. So now we need a way to lock these two radii of curvature together. We're going to use a formula for that too. So I'm going to call this formula achromat R. And I'm going to create a free variable which represents the radius, and I'm going to set it to 70. And then the formula is literally just going to be the free variable. The reason we create a free variable instead of just putting, say, 70 in the formula box is we want the optimizer to be able to change this. And to do that, we have to create it as a free variable. So now that I've created this formula, I'm going to go ahead and drag it above these two just because I like the order. Do a little bit more housekeeping. Okay, and now I'm going to set the radii of curvature to use this for both lenses. Remember, we rotate this 180 degrees, so it should be this one. I'm also going to add a little bit more spacing just so we have some room to vary these curves. And now, as you can tell, we've got no more overlapping. So both the NBK7 and the NF2 glass are touching each other. And if you were ordering a lens like this, this would typically be a cemented interface. So now that we've added our glass, we have our setup, we start getting ready to optimize. First thing we want to do is we want to change our display settings so that we hide these rays, which we're not going to use in our optimization, and we show our uniform infinite emission, which was the original one. So I'm going to go ahead and I'm going to start changing things. We're going to drop the opacity. I'm not going to show the hit markers anymore because we don't need them. Then I'm going to uncheck these guys and check this one. All right, so now I'm showing the last uniform infinite emission that we cast. Now this was before we created this element, I believe. So I don't think that it's affected by this element at all. So now we've got that ready so we can actually see the work as the optimizer churns. Now the next thing we need to do is modify our light path. Because we've added a lens, our old light path doesn't match that anymore, which means all the light we try to cast will be marked as stray. We don't want that, so we're going to go ahead and change the light path now. I'm going to increase the size of this panel so it's a little easier to see. I'm going to move the lens over, and I'm going to pick this surface here. This lets me know what surface is on this side. It's the left. So I'm going to go ahead and drag that by the detector. Then I'm going to manually create the right segment for revolution body 3. Let's go ahead and get that correct. Do I have the right segment? Yes, I do. I'm going to go ahead and drag that above. So now I'm going body 2 right segment to body 3 right segment, body 3 left segment to the detector. And that should be correct. Now as you can tell, the browser still has some red areas. Let's take a look at the first one, the merit function. We can see that it's red because the radius of curvature for body 2 is now bound to a formula and can no longer be varied. That's because we bound it to achromat R. So we need to go ahead and delete this. It can no longer be an optimization variable, and we need to add achromat R in. We still have one more free variable, and that's the outer radius of curvature of body 3. So let's go ahead and add that in too. Now, I'm not entirely sure where this is going to land. So I'm going to jack up the acceptable ranges for these values and let the optimizer do the work for me. Okay. So now I have set up our optimization variables. I've set up the valid ranges for them. We're still going to try to solve for collection efficiency. And let's see here. Do we have anything else? Nope, I think we're good to go. So there's our merit function completed. And I'm going to move this over so we can watch the cone while the optimizer is running. Now I'm going to open up the optimizer. It all looks good. I'm going to increase the number of evaluations so we have enough time to watch this work. And now, moment of truth, I'm going to run the optimizer. And here we go. And we're going to see it's going to make some changes. And it might not get to the solution immediately. Oh, there we go. Now we're at about, what, 1,500? Oh, we're still going. Still dropping. Okay, it seems that we have stabilized now at a merit of about 0.12. Now this took a while because we were casting a lot of rays. We could optimize this by decreasing the number of rays cast by uniform infinite. It would run a little faster. We could also choose a different method besides CMAES, but it only took a few seconds and we got the right answer. So let's take a look. Now as you can see here, that blue cone has entirely disappeared. And if we take a look at our collection efficiency, it's risen to about 82.17%. Now that's a lot better than where we started this video, which was around 70%. And we're now getting all of the blue light and the violet light into our optical fiber, which was our goal. Now the next question is, can we do any better than 82.17? The answer is, yes we can, but we have to be willing to pay a price for that. To better understand that, we need to quantify something called the Fresnel losses that are currently present in our system. Now, what is a Fresnel loss? Well, to understand that better, let's no longer hide the stray rays. As you can see, there are now rays of light going everywhere. And in fact, on a kind of per ray, not per intensity basis, there are a lot more stray rays than there are actual desired rays or intended rays. Let's take a look at one of them. I'm going to go grab this guy here. And I'm going to open the display panel. Sorry, I got a lot of panels going on. I'm going to make its opacity 100%. Now let's take a look at the path this ray takes. So first, it's coming in from the left. It passes through this surface, and then it intersects off this surface, bounces on the inside of the glass, finally exiting up here. Now it starts with an intensity of about 490 intensity units. With that first intersection, we lose about 20 units. Then we lose about 450 units of intensity, and that's right here at this intersection. Now what's happening here is actually most of the light is continuing straight through this lens and on to the next. But a substantial proportion of it is actually getting bounced back and becomes this ray that we're watching here. This phenomena, where most of the light is actually refracted through the lens and a smaller portion is reflected, is called Fresnel reflection. And the phenomenon as it relates to losing efficiency is called Fresnel loss. Now we can get a rough idea of how large the Fresnel losses are in our system. First, let me go ahead and put the opacity back down, turn the stray rays back on. So to do that, we're going to use a quick and dirty approximation for Fresnel losses. Now this formula only applies to flat surfaces and light that's hitting them at a normal angle of incidence. And it's given as a ratio of the indices of refraction between the two surfaces on either side of the interface. So the formula is as follows. Fresnel loss equals N1 minus N2 divided by N1 plus N2. And then the result is squared. Now we have three different kinds of interfaces. The first is in BK7 in air, the second is in BK7 in NF2, and the third is NF2 in air. So the in BK7 air loss is going to be equal to 1.516 minus 1 divided by 1.516 plus 1. And then the result would be squared. Whoops, I can't type. So that's about 4%. In fact, we can make that into a percent. I wonder if this will work. Yep, there we go. So now that's showing as a percent. Now, the next interface is the NBK7 NF2 interface. Now this is going to end up being a much smaller value because the indices of refraction are so close together. As you can see, this is only about 0.1%. And then finally, the NF2 air interface, this is going to be a larger loss because the index of refraction for NF2 is greater than NBK7 for a given wavelength. Oops, using the wrong value here. Let's use the right value. In units of percent. There we go. So now our total loss is going to be 3 times, because we have 3 NBK7 air interfaces, plus 1 times our NBK7 NF2 interface, plus 1 times our NF2 air interface. And of course I can't type. What was the issue here? Oh, whoops. NBK7. Fix that. Fix this. All right, so our total loss about 18%. And that would give us our rough estimate of collection efficiency maximum that we could hope to achieve would be roughly 1 minus the total loss. Now you'll notice that the value we got is very close to the results of our collection efficiency analysis. However, our collection efficiency analysis is actually slightly higher. Now how could that be? Well, if you'll recall, what I told you initially is this formula is only approximate. It only applies to light hitting a flat surface at an angle normal to that surface. We have curved surfaces and the light's hitting at a whole variety of different angles. Also, this formula only uses the indices of refraction of the different materials at the sodium D line, which is 589 nanometers. We have wavelengths of light all the way from 400 nanometers up to 700 nanometers. So this final value should only be treated as approximate. Nevertheless, because we're so close, we can conclude that our current design is limited by Fresnel losses, and any further optimization is likely to be a waste of time. But we could still do better. We can still get this number up. And to understand how we could do it, we have to understand this total loss formula. The total loss formula has roughly 2 components: the number of interfaces and the loss that we take at each interface. Now, if we wanted to reduce the total number of interfaces, that would mean removing lenses. And as we saw in the preceding videos and this one, each time we added a lens, the performance of our system went up. So decreasing the number of interfaces is probably not the right way to improve the overall efficiency of our system. That just leaves decreasing the loss at each interface. Now, one way we could do that would be to decrease the index of refraction of the 2 different types of glass that we are using, to bring them both down, to bring them closer to air. And this would work somewhat. But even if we opened up the glass catalog and started looking for things that were lower than NBK7, maybe in the 1.5 range as a maximum, we see that out of the, 500 materials that are in the catalog, only about 31 of them, many of which, like acrylic, we probably didn't want to use to begin with, have a lower index of refraction than in BK7. And we'll notice that the index of refraction of much of the ones that are lower, not really that much lower. We're still in the 1.4s. So even if we selected one of these different glasses, we still wouldn't have done that much to reduce our Fresnel losses. So there has to be another approach. And the other approach, the one that is commonly used, is called an anti-reflective coating. Now an anti-reflective coating does precisely that. It reduces, often dramatically, the Fresnel reflections at each interface. However, these coatings come with a cost. The first cost is that they just cost more money if you put them on your lenses. The second is, many of them are prone to damage. And the third is, they often only work over a range, sometimes a narrow range, of wavelengths. Nevertheless, in many cases, all of these costs are worth paying, and an anti-reflective coating is the right choice. However, for this design, we're going to declare 82% good enough. We're going to stop here, and we'll visit anti-reflective coatings in another video. Thank you very much for watching, and I'll see you next time.